For billions of years, our solar system has sailed through this cosmic sea, a small, glowing island of planets orbiting our sun. We have always felt a certain loneliness, the sensation of being alone in our celestial neighborhood. But what if a message in a bottle, a traveler from a distant shore, suddenly appeared? What if a visitor from another star system sailed right through our cosmic backyard? It is a thought that ignites humanity's deepest curiosity. It connects us to something far greater than ourselves, a vast and unexplored universe filled with possibilities we have barely begun to imagine. The cosmos is speaking and we are learning to listen. This is not fantasy. It is the frontier of modern astronomy. We are living in an era of unprecedented discovery, where our telescopes have become powerful enough to capture the faint whispers of these cosmic travelers. These objects, forged in the crucible of another star's planetary system, carry with them the secrets of their birthplace. They are time capsules that travel through the interstellar void for millions, perhaps billions of years, before their chance encounter with our sun. Their journey is a testament to the immense scale and history of the galaxy. Witnessing one is like receiving a postcard from an unknown world, a tangible piece of another corner of the Milky Way, delivered right to our doorstep. The arrival of a new interstellar visitor would send a shock of pure electricity through the scientific community. It is a fire alarm in the middle of the night for astronomers around the world. All other plans are abandoned. Every available telescope, from giant observatories on remote mountains to the powerful eyes we have placed in orbit, would turn its gaze to this single fleeting point of light. The race against time begins instantly. This traveler did not come to stay. It is merely passing through. Its trajectory, slightly curved by our sun's gravity, hurls it back into the darkness between the stars, never to return. We have one chance and only one chance to learn everything we can. This fascination is woven into our very being. It is the same impulse that led our ancestors to cross oceans, to climb mountains, and to look at the night sky and wonder, what is out there? Are we alone? An interstellar object is more than just a rock or a piece of ice. It is a profound reminder that our solar system is not an isolated bubble. We are part of a galactic ecosystem, a dynamic and interconnected web of stars and planets. Studying such an object is a form of cosmic archaeology, investigating the past not of our world, but of a world we have never seen, a sun we do not know. It is an opportunity to touch the unknown. What does it mean for something to be interstellar? Think of our solar system as a family home. The sun is the father, and the planets, asteroids, and comets are the children living there. They are all bound together by the sun's gravity, circling endlessly within the confines of our cosmic home. They were born here, and will likely spend their entire existence here. An interstellar object, however, is a visitor from a completely different home, a different solar system, with a different parent star. It is not bound to our sun's gravity. It is merely passing through, a tourist on a grand journey through the galaxy. Its trajectory is a hyperbola, a stretched curve that proves it has enough velocity to escape the sun's pull. These objects are exceptionally rare to see. The space between stars is almost incomprehensibly vast for a small object, perhaps only a few hundred meters or a few kilometers in diameter. To travel from its native star and by chance cross the path of our tiny solar system is an event of incredible improbability. It is like throwing a single grain of sand from a beach in California and having it land on a specific postage stamp in Japan. The fact that we have seen any of them at all tells us that the galaxy must be full of these wandering bodies, ejected from their own planetary systems during their chaotic formation. They are the cosmic debris of planetary construction projects happening throughout the Milky Way. What are these visitors made of? They can be many things. They can be rocky, like an asteroid, a fragment of a planet destroyed long ago, or they can be icy, like a comet, a frozen ball of gas, dust, and water from the frozen outer regions of another star system. As a frozen interstellar visitor approaches our sun, the heat would cause its ices to sublimate, transforming directly into gas. This process would create a bright coma, a diffuse atmosphere around the object, and potentially a tail pointing away from the sun. This tail is a gift to astronomers, as it allows us to analyze the chemical composition of a place we could never hope to visit. The journey of an interstellar object is long and lonely. After being violently ejected from its native system, it travels through the cold, dark void for eons. It is exposed to constant radiation from deep space, a process that can alter its surface, baking it into a dark reddish crust. It rotates on itself, a silent witness to the gravitational chaos that gave it its freedom. Its arrival at our solar system is a brief and fiery interruption in an otherwise tranquil existence. It is a fleeting moment when this ancient relic is bathed in the light of a new star, our sun, before continuing its lonely journey into eternal night. Our first confirmed interstellar visitor arrived in 2017. It was named Oumuamua, a Hawaiian word meaning a messenger from afar that arrives first. The name was perfect. Oumuamua was different from anything we had ever seen before. It was small, perhaps only a few hundred meters long, and strangely elongated, like a cosmic cigar or a flattened pancake. It was dark red, a color that suggested a long history of exposure to cosmic rays, but mysteriously. It showed no signs of being a comet. There was no diffuse coma or tail of gas and dust. Yet it was accelerating away from the sun, slightly faster than gravity alone could explain. This strange behavior generated intense debate and wild speculation. What was this object? The mystery of Oumuamua left us with more questions than answers. Could it be a new type of object we had never considered before? A nitrogen iceberg, a fragment broken off from a Pluto-like planet in another solar system? As it approached our sun, the frozen nitrogen would have turned into invisible gas, giving it a slight push without creating a visible coma. Others suggested more exotic ideas, including the tantalizing, though highly unlikely possibility that it was an artifact of extraterrestrial technology. Then just 2 years later, in 2019, a second visitor appeared. This one was named 2I/Borisov, in honor of its discoverer, amateur astronomer Gennady Borisov. Borisov was different. It behaved exactly like a comet we would expect to see. As it approached the sun, it developed a bright and beautiful coma and a long dusty tail. This was a crucial clue. It suggested that Borisov formed in a place that was very, very cold, even colder than the outer edges of our own solar system. They were like two completely different messengers from the great beyond. One was a strange, rocky enigma, and the other was a more familiar though still exotic icy comet. Together, they painted a fascinating picture. They showed us that the building blocks of planetary systems in other parts of the galaxy can be incredibly diverse. Some systems may produce rocky travelers, while others produce icy travelers with unique chemical fingerprints. They proved that these visitors are not merely a theoretical possibility, they are a reality. And they made it clear that we need to be ready because the next one could arrive at any moment, bringing with it a new set of clues about our cosmic origins. The discovery of a new interstellar object would likely not begin with a bang, but with a silent stream of data. It would happen in one of the world's automated sky surveys, such as the Pan-STARRS Observatory in Hawaii or the future Vera C. Rubin Observatory in Chile. These telescopes are robotic sentinels, tirelessly sweeping the entire visible sky every few nights. They take millions of images and powerful computer algorithms filter through that flood of data, looking for anything that has moved or changed. The software is designed to flag anything unusual, any faint point of light that is not a known star, planet, or asteroid. Most of them are just common objects from our own solar system. But one day the algorithm flags something special. It finds a point of light moving along a trajectory that is strange. It is moving very fast. Its trajectory is not a closed ellipse, the familiar loop of an object bound to our sun. Instead, its trajectory is an open hyperbola, the telltale signature of an object that came from interstellar space and is destined to return there. An alert is sent automatically to astronomers around the world. An email notification, a message that pings phones and computers in the middle of the night. A potential interstellar object has been found. The initial data is preliminary, but it is enough to ignite a storm of excitement and activity. The first hours and days are a frantic race for confirmation. Astronomers drop everything. They rush to book time on other telescopes, any telescope they can get, to take more photos and collect more data. They need to plot its orbit with extreme precision. Is it really on a hyperbolic trajectory? Could it be a mistake? Each new observation helps refine the object's trajectory, reducing uncertainty. Within a day or two, the verdict is given. The global astronomical community confirms it. The object is not from here. It is a true visitor between the stars. The discovery is announced to the world, and the real scientific investigation begins. This moment of discovery is a powerful reminder of what humanity can achieve when we work together. It is a global collaboration with observatories on different continents, coordinating their efforts to track the object as the Earth rotates. An astronomer in Chile can observe it until dawn, then hand off responsibility to a colleague in Australia, who then passes it to a team in Arizona. Data flows freely and openly, shared across international borders. The search to understand this cosmic messenger unites scientists from different cultures and backgrounds in a single shared purpose: to seize this fleeting opportunity to learn something new about the universe we all inhabit. Once the discovery is confirmed, the focus shifts from "where is it going?" to "what is it?" This is where the science of spectroscopy comes in. Telescopes do not just take beautiful pictures, they are actually sophisticated scientific instruments that can dissect light. By passing the faint light of the interstellar object through a device called a spectrograph, astronomers can spread it into its constituent colors like a rainbow. This spectrum is not smooth, however. It is crossed by dark or bright lines, which are like a chemical barcode. Each element and molecule absorbs or emits light at very specific wavelengths, creating a unique pattern. We can read this barcode to discover what the object is made of. If the object is a frozen comet, this analysis becomes even more exciting. As the heat of the sun vaporizes its surface, it creates a cloud of gas, the coma, around the object. Sunlight shines through this gas, and the molecules inside it leave their fingerprints all across the spectrum. We can see the signatures of water, carbon dioxide, ammonia, and methane. But we are looking for more than that. We are looking for complex organic molecules, the carbon-based compounds that are the building blocks of life as we know it. Finding these molecules in an interstellar object would be profound. It would provide strong evidence for the idea that the raw ingredients for life are common throughout the galaxy, delivered from one star system to another by these wandering comets. Beyond their chemical composition, we want to know about their physical properties. What is its size? What is its shape? How fast is it spinning? Answering these questions requires careful observation of how its brightness changes over time. If the object is tumbling or has an irregular shape, its brightness will fluctuate in a predictable pattern as it rotates, reflecting different amounts of sunlight in our direction. By monitoring these subtle flickers of light over hours and days, we can build a simple model of the object. Is it round like a ball, or is it elongated like Oumuamua? Is it spinning every few hours, or is it in chaotic rotation? Each piece of data is another brushstroke in our portrait of this alien object. The color of the object also tells a story. Just as the reddish hue of Oumuamua suggested a long journey through interstellar space, the color of a new visitor can provide clues about its surface and history. A dark reddish surface may suggest that it is rich in organic compounds that have been baked by eons of cosmic radiation. A more neutral or bluish color may indicate a fresher surface, perhaps recently exposed by a collision or some other activity. By combining all this information, its orbit, its composition, its size, its shape, its spin, and its color, we can begin to piece together the life story of this cosmic traveler and understand the environment in which it was born. Studying an interstellar visitor is not just about the object itself. It is about what it represents. It is a physical sample from another planetary system. We have spent billions of dollars building spacecraft to travel to Mars, Jupiter, and the asteroids in our own solar system to collect samples and study them up close. But here, the universe is delivering a sample to us for free from a place we could never hope to reach. It is an unparalleled opportunity to perform a kind of remote geology and chemistry on a world orbiting another star. This single object could provide more direct information about the composition of another solar system than decades of observation of its parent star, which is light years away. The chemical composition of the visitor is a crucial clue to its origins. Each planetary system forms from a giant cloud of gas and dust with a unique chemical cocktail. By analyzing the proportions of different elements and isotopes in our interstellar guest, we can compare them to our own solar system. Does it have a similar amount of water? Are the types of organic molecules the same ones we find in comets from our own Oort cloud? If the answer is yes, it suggests that planetary formation processes and the basic ingredients for life may be universal. This would strengthen the idea that planetary systems like ours are common throughout the galaxy. But what if the visitor is fundamentally different? What if its chemistry is truly alien? Imagine we found an object with a composition completely unlike anything in our solar system. Maybe it is extremely rich in a certain heavy element, or maybe it lacks molecules we consider common. This would tell us that the galaxy is a place of incredible diversity, with planetary systems forming under a wide range of conditions, creating worlds and objects we can barely imagine. This would challenge our models of planetary formation and force us to think more broadly about what a normal solar system looks like. Each new visitor adds another data point to our understanding of galactic demographics. Ultimately, the study of these objects connects to one of the deepest questions we can ask. Are we alone? Comets and asteroids would have delivered water and organic molecules to the early Earth, potentially jump-starting the process that led to life. If interstellar comets are also rich in these ingredients, it suggests that the seeds of life could be transported between star systems. This idea, known as panspermia, is no longer pure science fiction. While it does not mean that life itself is hopping between the stars, it does mean that the fundamental building blocks for life could be scattered throughout. Our interstellar visitor is a piece of that great puzzle, a clue to whether the cosmos is predisposed to create life wherever conditions are right. The most challenging aspect of studying an interstellar visitor is the harsh reality of time. This is not a leisurely investigation. From the moment it is discovered, the clock is ticking. The object is moving at incredible speeds, often tens of kilometers per second. It will cross our solar system in a matter of months. With each passing day, it moves farther away. As it recedes from the Earth and the Sun, it becomes fainter and fainter, rapidly disappearing back into the darkness from which it came. This creates a profound sense of urgency in the scientific community. We have a very small window of opportunity to observe it, and we must make every second count. This urgency drives a rapid and intense period of scientific activity. Proposals for telescope time that normally take weeks or months to review are approved within hours. Observatories can even activate target of opportunity protocols, postponing other scheduled observations to prioritize this unique and time-sensitive event. Scientists work around the clock, analyzing data as it arrives, sharing results in near real time through online forums and email lists. The goal is to learn as much as possible, as quickly as possible, so that follow-up observations can be planned to answer the new and more urgent questions that arise. It is science in its purest and most dynamic form. The ultimate dream for many astronomers would be to send a spacecraft to intercept one of these visitors. Imagine a small, fast probe, perhaps launched on a powerful rocket, on a mission to chase the interstellar object. It could pass by it, taking high-resolution images and analyzing its composition up close, with far greater precision than any telescope on Earth. This is an incredibly difficult challenge. We would need to detect the object early, when it is still far away, and then quickly launch a mission on the perfect trajectory to reach it. Though we have not gotten there yet, space agencies like NASA and ESA are already studying the feasibility of such a rapid response interception mission for the future. For now, we remain Earthbound observers, watching these messengers from afar as they pass by. The brevity of their visit is what makes them so precious. It is a powerful lesson from the cosmos about the nature of moments and opportunities. We cannot pause. We cannot ask the visitor to wait while we prepare our instruments. We must be prepared, vigilant, and ready to act. The fleeting nature of its passage underscores the importance of our continued investment in astronomy, in building better telescopes and more sensitive detectors. Because the next visitor might be the one that brings the answer to a question we have been asking for centuries. The discovery of an interstellar object does more than just provide scientific data. It touches something deeper within us. It is a moment of connection with the broader cosmos. For a brief period, an object born in a completely alien environment that traveled for millions of years through lonely darkness shares our sky. It is a physical link between our home and another star system unknown to us, many light years away. Looking at the sky, knowing that one of those faint points of light is a traveler from another world, can evoke a powerful sense of awe and perspective. It makes the universe seem a little less empty and a little more like a dynamic, interconnected neighborhood. This cosmic connection inspires us to continue searching, to continue questioning. Each discovery like this feeds our collective imagination and our desire to explore. It reminds us that there is still much we do not know. The universe is not a static, unchanging backdrop. It is a place of constant motion, of epic journeys and chance encounters. We are privileged to live in an era when we can witness these events and begin to understand their significance. These discoveries belong to everyone, not just scientists. They are part of the shared story of humanity's journey to understand its place in the cosmos. They invite all of us to be curious explorers. The study of the universe is a journey of humility. Each new piece of information, each visitor from the void, shows us how much more there is to learn. We are only just beginning to scratch the surface of the great mysteries of the galaxy. There are probably countless other interstellar wanderers passing through our solar system right now. Most of them are too small or too faint to be detected with our current technology. But as our telescopes become more powerful, we will undoubtedly find more of them. Oumuamua and Borisov were only the first two voices of what may soon become a cosmic chorus, each singing a different song about their distant origins. So the next time you look at the night sky, take a moment to think about it. Somewhere out there, perhaps even passing through our solar system right now, is another piece of a distant world, a silent messenger on an ancient journey. And with each passing year, our ability to see these visitors grows. The search for knowledge is infinite, and the cosmos is the greatest library of all. The history of the universe is written in the stars and in the space between them. And we have only just begun reading the first chapter. The best is yet to come.